Hey everyone, I wanted to make a quick video for you. I'm also going to send out my worked solutions to the 2.4 in class, but I wanted you to have a video as well. So we did not get to part D in number one or number two in class today. So I wanted to kind of work through these. Okay, so if we are looking at part D of number one here, m of x equals e to the x over x squared plus 1. Okay, so we have a quotient of functions here, so we're going to make sure the we're going to see where the top and bottom functions are continuous, and then we also need to figure out where the bottom does not equal 0, right? Because a continuous function divided by a continuous function is only continuous if the bottom does not equal 0 as well. That's an extra thing we have to be careful of when we're dividing functions. So on top here, e to the x, where is that continuous? Well, e to the x, that's an exponential function that looks like this. That's continuous everywhere. Right? Negative infinity to infinity. That's good everywhere. So we don't have to worry about the top. And then the bottom, x squared plus 1, that's a polynomial. So we are continuous, again, everywhere from negative infinity to infinity. So the top is continuous everywhere, the bottom is continuous everywhere. So what that means is this entire function, the top divided by the bottom, will also be continuous everywhere as long as the bottom does not equal 0. So the whole thing is continuous where x squared plus 1 does not equal 0. Okay, so let's figure out where x squared equals 1, and then we can just get rid of those parts because those are the places where we will be discontinuous, right? If the bottom equals 0, that's where we would have a vertical asymptote, and we would have an infinite discontinuity there. So let's see where we have infinite discontinuities. So x squared plus 1, we're going to set that equal to 0 to figure out where our discontinuities are. That's going to be x squared. That's going to be where x squared equals negative 1. And so here's where you would try to take the square root of both sides, but something weird happens. I can't take the square root of a negative 1. You're right. So what that means is that either everything works or everything doesn't work. So question is, what works here? If I plug any number I want in, how about 0? 0 squared, is that negative 1? No. What if I plug 1 in? 1 squared is 1. That's not negative 1. What if I plug negative 1 in? Negative 1 squared is negative 1 times negative 1. That's positive 1. There's no solutions to this. Nothing works. There aren't any places where x squared is equal to negative 1. So what that tells us is that we don't have any places where we're discontinuous. We don't have any vertical asymptotes here. That means we don't have any discontinuities. There we go. I can spell. And that means this entire thing is continuous from negative infinity to infinity. Everything works everywhere. The bottom's never going to be 0. The top's continuous everywhere. Bottom's continuous everywhere, which means this entire function is continuous from negative infinity to infinity. If there had been a place down here, if this had been x squared equals 1, in that case, we would have had vertical asymptotes at plus and minus 1. So we would be continuous everywhere except 1 and negative 1. And then you would write that out in your intervals. Negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. Right? We would just cut out the places where you're discontinuous. Okay. Okay, so then the last one, find the value of c that makes this piecewise function continuous. Okay, so we talked about piecewise functions a little bit on Friday. So in order to have a piecewise function be continuous, I need the two ends of this to come together, right? I need them to match. Um, and I know this isn't exactly what my function is going to look like, but are you okay that our breaking point is 5, right? We're going to look like one function on this side of 5, and then we're going to look like another function on that side of 5, right? If in order for this to be continuous, I need these 2 points to be exactly the same. So really what that means is that I need the limit as x approaches 5 from the left of this function to be equal to the limit as x approaches 5 from the right of this function, right? If these two limits were the same, then this point and this point would be the same, and we would overlap. And oops, sorry, I don't know what that's doing. Okay, so then these two would overlap, and we would look something like this, I think. So they would come together like that. Again, and this might not be a perfect graph of that or anything like that, but we're trying to get these two pieces to match. Okay, so in order for this function to be continuous, I need the limit from the left to be equal to the limit from the right. Okay, well, if I'm going to take the limit as x approaches 5 from the left of this function, well, if I'm to the left of 5, then I'm at places where our x values are a little bit less than 5. That means I'm in here, which means my piecewise function is going to look like x squared minus c. So if I'm going to find the limit as x approaches 5 from the left, I'm going to use this function. And then if I'm looking at the limit as x approaches 5 from the right, well, the limit as x approaches 5 from the right. These are x values where x is a little bit bigger than 5. That means if x is bigger than 5, I'm going to be down here, and I'm going to use this function because that's what my function is going to look like over here where x is a little bit bigger than 5. And so since I need the left-hand limit to be equal to the right-hand limit, we're going to evaluate each of these and make sure that they are equal. So the limit as x approaches 5 from the left of x squared minus c, well, in order to evaluate this limit, the limit as x approaches 5 of x squared is going to be whatever 5 squared is. And then I'm going to have minus c because the limit as x approaches 5 of c is c. And I'm going to evaluate this limit over here on the right. The limit as x approaches 5 from the right of 4 times x is 4 times 5. I'm just plugging that in. And then the limit as x approaches 5 of 2 times c is whatever 2 times c is. So this is my limit from the right. This is my limit from the left. And now I need to make sure that they're equal, so I'm going to solve this equation. So I'm going to have 25 minus c is equal to 20 plus 2c. I'm going to put all my c's on one side, anything without a c on the other. I'll put my c's on the left. I think that's where I'm most comfortable, so I'm going to move my numbers over here. And so I'm going to get negative 3c is equal to negative 5. Divide both sides by negative 3, and c is going to be positive 5/3. That is the solution to this problem. A value of c of 5/3 will make this function continuous. Now, how can I make sure that I got this right? Well, let's check it. Using a C value of 5/3, I'm going to go through my continuity checklist and make sure that we are continuous at x equals 5. So the first thing that I need to check on my list is, does f of 5 exist? Well, f of 5, if my x value is 5, that means I'm going to be in this situation on the bottom, and my function value is going to be whatever 4 times x, which is 5, plus 2 times c, and we just found that c was 5/3. If I put that in a calculator, I'm going to get, let me just put this in here real quick, and I get 70/3. Okay. And then we have to make sure that the limit as x approaches 5 of my function exists. Well, in order for that limit to exist, we have to check the two-sided limit. Limit as x approaches 5 from the left is going to be the limit as x approaches 5 from the left, again, of x squared minus c, which is 5/3. That limit is going to be 5 squared minus 5/3. And again, when I put that into my calculator, I get 70/3. That's the limit as x approaches 5 from the left. Now let's check the limit as x approaches 5 from the right. Sorry, I didn't leave myself enough room here. The limit as x approaches 5 from the right of my function. Well, that's going to be the limit as x approaches 5 from the right. Again, from the right, x is a little bit... Oh, I got these backwards, didn't I? No, I'm good. As x approaches 5 from the right, sorry, I'm a little bit bigger than 5. I'm down here. I'm going to use 4x plus 2 times c, which is 5/3 here. And the limit as x approaches 5 of this is going to be 4 times 5 plus that 10/3. And when I put this in my calculator, I get 70/3. Okay, so what is the two-sided limit? Does it exist? Yes, limit from the left was 70/3, limit from the right was 70/3. That means my two-sided limit is also 70/3. And the last thing on my checklist is, are these two equal? They are, and that is the third thing on my checklist. So we are, in fact, continuous at x equals 5. So basically, with all of these, you're going to see a handful of piecewise functions in here. I want you to make sure that your left-hand limit is equal to your right-hand limit at every breaking point of your function. And when I say breaking point, really what I mean are the places where you have the same number up here and down here, right? It's the places where they break. Um, and so we have a break at 5. So here we had to make sure we were continuous at 5. You might see a piecewise function where you have more than one break. You would do the limit from the left and the limit from the right at each of your breaking points and make sure that you get the same C value. Okay, I hope that helps with your homework. You have until Wednesday, which is January 24th to finish this. I think I said Thursday in class, but I also said January 24th. I just had the day of the week wrong. It's actually a Wednesday, not a Thursday. So this will be due on Wednesday at midnight. Let me know if you have any questions. Other than that, happy homeworking.